Good morning, everyone. Good evening, everyone. Welcome to a new episode of Aero Campus, Aerotalks with a new guest talking about a new subject, new interesting subject. Here we are, today we are having Raymond Stott from Space Specialists from a company based in UK and Australia. He will be talking about space robotics, and hopefully tomorrow he will be talking about environmental testing of satellites. So I wish you a good present. I wish you good luck, Mr. Raymond, and hopefully for all of you, dear participants. السلام عليكم، مرحبا بكم اليوم في لايف جديده من ايروتوكس، من لا سيري تاعنا ايروتوكس. اليوم جبنا لكم ضيف جديد راح يكون حاضر معنا اليوم او غدوه ان شاء الله، راح يحكي لكم على سبيس روبوتكس، وثانيك راح يحكي لكم غدوه ان شاء الله على environmental testing of satellites. Raymond Stott from UK, from a company named, he's the founder of Space Specialists, company based كما قلت لكم based in UK and Australia. So without any further ado, I will pass the everything to Raymond to present himself and start the presentation.
Thank you very much, Ramzi. Can you hear me okay?
Yeah.
That's great. So first of all, I'd like to welcome everybody this evening. Marhaba bekum. With me, Raymond Stott. I'm from the UK, Space Specialists, and we have an office also in Australia. Wesh Rakom, Raku Lebes. And I hope everybody, hope my accent is okay for the pronunciation. So thank you very much. And I'm going to share my computer now for the presentation. So just start. So is everything okay? You can see, Ramzi?
Yeah, everything's good.
Perfect. So welcome, everybody. I'm going to be talking about robotics in space. And I've been in space for about 30 years. The industry is very dynamic. And yeah, I'm very excited to showcase future, past and present robotics, but it's all about guiding you about robotics in space. So my background is I'm from the UK, and I studied at Loughborough University. And my first job was at a company called British Aerospace. They have now changed name. They're called Airbus, all across Europe and the world, based near London. So that's where I studied, and I studied mechanical engineering. My background is space. So I've been very fortunate to spend most of my career in the space sector, mostly outside of the UK, working in different places around the world. Here you can see some of the different companies and organizations I've worked in. For example, the European Space Agency, ESA, that's in the Netherlands. CNES, that's in France. I'm working in French Guiana, in Kourou, the launch site. I've also worked at OHB Antwerp Space in Belgium, and also in Thales Alenia Space in Italy, in Rome. So these are some of the locations where I've worked. I'm quite a different Brit. I managed to speak some poor English, but I'm very proud to have picked up these languages. Donc, en cas de besoin, on peut basculer en français. On a vraiment étudié à l'école, et après ça, sur place, j'ai appris mon français soit à Toulouse, soit en Guyane, aussi dans le monde entier, aussi à Montréal, au Canada. So I'm also able to speak some notions of those other languages. My background is 30 years, I said, and 3 years ago, we set up the company Space Specialists. We have an office in the UK. On the left, you see I'm in the northwest of England, near Chester. That's in between Manchester and Liverpool. And also we have an office in Australia. That's the Gold Coast there. We're also going to have an office in Adelaide in South Australia. Space Specialists is a company with 3 objectives. We provide expert consultants in the space business, everything to do with satellites, rockets, and ground segment, but also the downstream, as we call it, the products and services from space. We also recruit. We put people in space jobs worldwide, both contract and permanent. So if you're looking for a position, we advertise jobs on our website. And also we do training and talks. We do online training just as much as on-site training, again, in technical and commercial subjects, everything to do with space. We've recently launched a new initiative due to the coronavirus pandemic. It's called Spacemates Online. We're very pleased with this. It's every Tuesday between 11 a.m. and midday UK time. And we have different guest speakers, and it's a regular networking event only for space. So if you want to get in touch with people around the world with space, please come along. You can see here, it's an online format, and we have different guest speakers. You can see some past speakers here who've talking about rockets, the ground segment, Mars, activities in Wales, and also space law. So we have quite a diverse crowd, and we have people from the UK and Australia and worldwide. Next week, we have my very good friend, Isla Raquel. Next Tuesday, she's talking about nanosatellites, and she'll be talking about her program and project for Brazil. They have some hyperspectral images in those CubeSat style satellites that they're going to be launching for Brazil. And we're going to be interviewing her next Tuesday. So if you want to meet her, ask her some questions directly, come along, and we're very much interested to see you. So ever since I was a child, I've been fascinated by space. It permeates you through TV, science fiction. And of course, very early on, I talked about robotics. I was watching these sort of programs. It all stems from science fiction and on the TV. And today we're going to be talking about space robotics. So I presume you've heard about different robots in the media. You've obviously heard about Star Wars, Disney films, more recent ones, and the original Robbie the Robot. So these robotic ideas influence how we do things today, but it also gives us room to dream. And there on the left is one of the first robot films, and there on the right is probably a more recent one from Star Wars. So these things have permeated our psyche, and we understand different things about robots. But tonight I'm going to show you about space robots in particular, and some of the developments that I've been working in and what's happening in the world. So what is a robot? Well, a robot is a thing different to different people. It's a machine. It can be programmed by a computer, and it's also able to carry out different complex tasks. So you see an early drawing there of a very interesting robot. It's still a robot, and you could call maybe a plane or a satellite or a probe that goes into space also a robot. What you have to understand is it has different external control devices, and they can also have that control inside them as well. So they might be controlled, or they might have the control themselves. You can have robots in human form, but most robots are designed to do the task. So you see industrial robots in factories, or you'll see different robots for doing different activities in, say, medicine, or in different high-tech engineering, but also in space. And it depends on the task, and that's what we do. Here's a robot here on the left. It's an interesting design. It's actually on an ice sheet, and it is able to go underwater, so it can go on ice and on ground. And the key thing about space robotics is to understand what the space environment is. So the robots don't have to work on the ground, they have to work in space, and the space environment is very harsh. So you have vacuum, there's no air. You also have extremes of temperature, and depending where you are in space, you have to survive that environment, which can be quite harsh on the mechanical systems, the electronics, but also the materials you make the robot out of. So when we talk about space robotics, we're talking about mechanics, electronics, and computers, mechatronics, and that enables you to understand how to make robots that will survive in space. And these robots that move around need to understand their environment. So they need to have sensors. It could be a sun sensor. It could be a temperature sensor. So different sensors are used. Could be a star sensor, could be a light sensor, or it could be a sensor to do with a certain activity. And then depending on the sensors, the brain of the robot or the controller externally would actuate the robot to move around or do some useful activity. So therefore we have this thought of control, control can be completely autonomous. That means the robot has its control itself, or it can be controlled by humans, and we call that semi-autonomous. One thing that's very important to understand about robots is a concept called degrees of freedom. That's the number of independent movements that a robot can make. And if you think of your arm can make an up and down movement at the elbow. That's 1 degree of freedom. And then on the wrist, you can do almost pitch, roll, and yaw. You can't quite do perfect roll. So these different movements are the numbers of degrees of freedom or joints that you have in a robot that it can have. So it's good to understand how many degrees of freedom a robot has and how complex a robot needs to control its joints. I think everybody's remembered the space shuttle. Well, there's a very famous robot on there. It's Canadarm that brings the payloads out of the payload bay once the doors open. So I think everybody's seen that supplied from Canada. And that robot is controlled by the astronauts inside the space shuttle, and obviously is able to move around in space. It's very lightweight. And in fact, if it was on the ground, it wouldn't be able to support its own weight. But in space, it's perfectly at home, and it's able to cope with the extreme heat and cold environment, and also the vacuum of space. And you can see the different joints there on the Canadarm. So it has a different numbers of degrees of freedom. The International Space Station is in orbit above us. It's about 100 miles above our heads now, and that has a number of robotic systems on there. Canadarm 2, the bigger version of the Canadarm, but also Japanese robotics and lots of other robotics as well, which I'm going to show you. So here the International Space Station is shown with astronauts doing their EVA or spacewalk, and the astronauts work with robots either through an astronaut inside the space station or using somebody on the ground who helps control that while they're working on the International Space Station. So really working together in what we call cooperative robotics. So when you see the astronauts working, they may be with their colleagues, or they may be working with robots. And this is the way we see robots working in space, together with astronauts and also on their own. So here you can see the DEXTRE. It's a dexterous robot that is attached to the International Space Station on the top right-hand corner. And you can also see Canadarm 2. That's the big arm that moves things around in space. And these two robots are on the International Space Station, flying around the Earth. And you can see a beautiful view of the aurora and the Earth's surface there. So these are the robots on the International Space Station. Here you can see DEXTRE or SPDM. There's some acronyms there. SPDM stands for Special Purpose Dexterous Manipulator, and the ISS is the International Space Station. And the SPDM is a dexterous robot that can do tasks on the space station controlled by the astronaut inside or from the ground. And it's another multi-axis controlled robot that can do activities with or without the astronauts outside the space station. And it's generally used for maintenance on the International Space Station. And here you can see it connected to the Canadarm 2, which is connected to the module there at the top. And that connection provides you with the power and data that you can allow the robot to do its task. And here on the right-hand side, you can see the battery being removed from one part of the International Space Station. It's a bit dark. That's because the space station goes around the Earth in sunlight and eclipse. And in this time, they've used the station lights to see the activity. The robot also has lights on it to make sure it can see the task, etc., as it's doing the maintenance. Here is some other aspects of the International Space Station. Here you can see the cupola, or the window to space, and also the inside of the cupola. You can see some computer screens and also what we call the robotics workstation. And there the astronauts control that robot, the SPDM DEXTRE, but also the Canadarm 2. and they can see activities from the great windows that you can see there, and then they can safely do robotic operations using a joystick and also the computer keyboard. And they've recently demonstrated remote control also on planetary surfaces by a simulation by controlling a rover on the ground. Here you can see a test setup in Europe, and they're controlling the rover and doing some activities as if they were on the moon. So these are some of the things that you can do as an astronaut from the International Space Station. I'm just going to show you a very interesting video clip that I'm very happy to show you, and it's about the robotics just recently on the station.
There they are.
We copy and concur.
And that's 200 meters from the center line of the space station. And as soon as I get inside of 200 meters here, I'm going to switch to a different reference point, and we'll reference from the docking port.
We do plan to hold briefly at waypoint 2, so reminder that crew visors down are not required until the ground is preparing to commence the final approach. Down.
They're sitting right there, 20 meters from the docking port. One more view.
SpaceX Station Dragon on the Big Loop. We are inbound from approach 2.
Dragon arriving. The crew of Expedition 63 is honored to welcome Dragon and the commercial crew program to welcome aboard the International Space Station. Bob and Doug, glad to have you as part of the crew. Well done. Bravo Zulu.
Never copy. Thank you, Chris.
Okay, so hopefully you can see that the International Space Station has these robots. Great piece of video there with the recent Crew Dragon docking to the International Space Station, and you saw these DEXTRE and Canadarm 2 in the foreground, with also some docked vehicles that they service and also capture and allow docking activities to occur. Here's another shot of the outside of the Columbus module. That's the European contribution to the International Space Station. And you can see some of the lower parts of the DEXTRE robot there with some equipment on it that they're using to exchange some equipment on the Columbus module. Here's another shot of the Canadarm 2 attached to the International Space Station, also holding on to DEXTRE. It's quite a complicated robot. It looks a bit like a large human, actually, with 2 arms, a waist, and a head, which is basically coupled up to the end of the Canadarm 2. And with this complete arrangement, you're able to service smaller items on the International Space Station without going out for a spacewalk. So robots can help save time, and also in dangerous environments, they can really help the crew concentrate on other things which maybe are more critical. So these are some of the International Space Station robotics that you see. This is a close-up of the robotic end effector, probably about the middle of your screen, and it's holding on to this panel. And here you can see that it is moving that panel for installation onto the outside of the Columbus module. So robotics have different cameras. It has actuators and joints and sensors to be able to move this around in space. And remember, space is vacuum, different temperatures, and that's why you see some of the thermal protection of these white thermal blankets. or other areas are painted with different paints, or they have reflective coatings on. So this is a close-up of the robotic operations that are happening on the ISS. Here's another one. SPDM DEXTRE is moving that module there. It's probably a big, I think it's a power conditioning unit, and the two arms are used to exchange that, and the robot moves around on the outside of the station to replace these items for maintenance. Here's another shot of the assembly, quite complicated assembly, and there you see a docked Crew Dragon or another resupply vehicle that's also in. And here's a close-up of the SPDM DEXTRE attached to the module of the International Space Station, and you can see the arms clearly, the joints. Around the joints you can see cameras, and also in the body you can see about middle of it, it has a big joint, which means that it can completely rotate itself around. And it's quite a large structure, so this is probably the size of a small car, and this is the robot that exchanges units called orbital replacement units on the outside of the ISS. And here's another shot. You can see it attached again to the outside of the Columbus module near there. Also the Japanese module Kibo is in view, and there you see the Earth underneath. So these are different views of the robots against the Earth, and the astronaut is controlling that either from the ground or from the robotics workstation inside the cupola, that window onto space. And here you see some more shots of the SPDM DEXTRE, and there on the right hand side you can see Canadarm 2, which is plugged into another what we call grapple fixture. So the grapple fixture is where the arm has its base, and it can inchworm around the International Space Station, and with that it gets its power, data and video. So in order to control the robot, that's where all the links are made, and when you move around you have to have an end effector that will grab different interfaces, and you can see one there at the top of SPDM. It grabs the SPDM through that power and data grapple fixture, or PDGF. So there's a robotics workstation inside the space station. Here you can see yours truly practicing in Houston some of the activities that we train the crew. So we train the crew and also the flight controllers how to use the robots in space before they fly, and that way we can train them to be doing safe operations. The robotics workstation has hand controllers and cameras that they see the operations, and we make sure that they do safe controlled operations. And here you can see the type of work environment that the robot has to work in. Here are the big solar panels, the radiators. It's quite a complicated area, and you have to have a good situational awareness in order to operate the robot safely. So you have to know what you're doing, and you have to be trained before you use the robot. There you can see some boxes there sticking out of the truss structure on the left-hand side. Those are orbital replacement units. They are designed to be handled by astronauts and robots, and so robots can pick them up. They can unscrew them, move them around the International Space Station, and replace and exchange them. So this way, we've designed the International Space Station to be repaired by humans in a spacewalk, but also using the robotics on board. Here's a big vehicle arriving at the International Space Station. It's called the HTV, and that has been recently launched from Japan. And the big arm has grabbed that and docked it to the International Space Station. So the robotics are also used to do what we call big opportunity activities, as well as dexterous operations with the other robot that you see there. I've been very fortunate to train and help with robotics in Canada and America. So I was working with Chris Hadfield when he was working on the International Space Station, and when he was doing his EVA training, and also in the pool in Houston, in Texas, in the USA. They're working with the astronauts where they train in the neutral buoyancy laboratory, which simulates the spacewalk. And there you can see preparations with the astronauts as they go into the pool. Also in Europe, we have a European robotic arm, which will be launched very soon onto the International Space Station, the Russian segment. This arm is here on a flat floor in Leiden in the Netherlands. It's built by EADS Airbus Dutch Space. And we were testing the arm because it cannot support its own weight on Earth before we fly it into space. And here we're also showing what the concept of how that arm will look like, the European robotic arm or ERA, and how it will work moving equipment in and out of airlocks, but also moving astronauts and cosmonauts around on the International Space Station. Here you can see another view side of the International Space Station with the Crew Dragon recently docked on the right-hand side. And all of this workplace is where the robot has to work. So it has to have really good sensors, cameras, and vision systems to make sure it does activities safely. And we also need to make sure that the robots don't endanger the crew inside. You can also see in the gold and the solar panels, the HTV vehicle also docked to the International Space Station. We do training with the astronauts also underwater in Russia. So here we were training the European astronaut Andrei Kuipers in the European robotic arm activities in the Orlan spacesuit. And that's underwater in the pool in the Gagarin Cosmonaut Training Center near Moscow. And here I'm working with Andrei, helping him understand how to do robotic repair operations in case he needs to do that in space. Now, there are other robots in the International Space Station. I've put a few on here. On the left, you can see a personal assistant robot helping the crew interact and give them guidance and procedures. On the right is a companion robot that one of the Japanese astronauts brought with them into the ISS. On the left, down on the bottom, you've got the spheres. These are robots controlled by school children and students, and they're developing these inside the space station to dock around, and they use gas thrusters to control their movement in the weightlessness of space. And also you can see a robot working there inside the pressurized module. It's called ROBONAUT. It's similar to a human, and that robot is doing some tasks also controlled from the ground inside rather than outside the ISS. Here on the left, you can see ROBONAUT, and that's in comparison to the robot DEXTRE SPDM that I showed you some pictures earlier. So these robots can be humanoid, or they can be similar to robots you see, industrial robots. It depends on the activities they have to do. Here's another view of a concept of ROBONAUT in deep space, and also ROBONAUT inside the space station doing some activities. You'll notice it has some fingers and a bit like a hand. So they're trying to make the interface similar to what an astronaut would have. And astronauts and people around the world are developing exoskeletons in order to help us control robots remotely. Here you can see a colleague of mine at the European Space Agency in the Netherlands, and he's developed this exoskeleton with the team in the European Space Agency, and they're practicing using this to control a robot walking around on the outside of the Columbus laboratory on the handrails. And this way we can interact with robots and control how they do things from a distance. Here's another robot that was designed in Europe. It's called EUROBOT. And here we are practicing with a model of it that is designed to go in the pool in the European Astronaut Center in Cologne in Germany. And we used this test device to see how we could work with astronauts on the outside of the International Space Station. And we could allow the robot to control itself, and also we could control it with exoskeletons and practice removing ORUs, orbital replacement units, you see on the top right-hand side there. But also we tested it underwater. The bottom right is the robot in the pool, and we also had an astronaut dive with that. So we practiced this on the ground. Now, moving on to Mars. We've probably all heard about Mars, and it's very topical this month. There are 2 missions going to Mars. Robots are also on Mars. We have landers, we have small landers, we have rovers, we have static devices, and we also have satellites around Mars. These are all different types of robots. And you may have seen some of these in the press. Some are fixed, some move around. Here you can see some being delivered to Mars with a sky crane and other things. So I'd like to show you that SkyTrain movie, which is very interesting to see. And I'd just like to show you that movie now. So just bear with me a moment.
About 100 meters a second.
So far, it looks a lot like any other Mars landing. But now, things take a strange twist.
Go into a powered descent mode. We descend for the last 2 kilometers, look at the ground with the radar, and then about 20 meters from the surface, we employ our touchdown system, which is called the Sky Crane. We deploy the rover. We are still maintaining a constant vertical velocity. We touch down, cut the rover free, and fly off. It is a new architecture, and frankly, it looks crazy. It looked weird. It looked scary. Very crazy, wacky thing. And it looked like that to the folks at NASA headquarters. And so we went through what ended up being close to 2 hours. There's lots of questions, there's probing.
They ask about the airbags that worked so well last time. But this rover is 5 times heavier. Airbags would have to be impossibly huge. So that's out. What about a traditional lander with legs?
Legged landers, a la Viking.
With a heavy payload, it would be unstable, especially if it happened to land on a slope.
And that's one of the reasons that we don't like it.
The Sky Crane, though, can drop the rover anywhere it can drive.
It utilizes the rover's inherent terrain hugging capability. And the rover is placed in a condition ready to rove.
By the end of the day, the head of NASA was convinced.
So that video is fantastic. It shows you how the rover is deployed onto Mars using this Sky Crane. All of these things are robotic devices. They're amazing pieces of equipment, and you may have seen that before. If you haven't, it's a fantastic video to watch. Go and check it out on YouTube. But when we put a rover on Mars of such a heavy mass like Opportunity or Perseverance, which is about to be launched this month, very exciting this month, we're going to have a twin of Opportunity launch and land on Mars in this year. And these rovers, here's another picture, are assembled in clean rooms, very complex robotic devices, and they operate autonomously or semi-autonomously. Remember right at the beginning, talking about autonomous or semi-autonomous operations. And on that rover, you can see there are sensors, there are actuators, it has a brain, it has a computer, it's designed for the environment, it has mechanics, it has electronics, and it has computer science, all at the heart of mechatronics that help it work in the extreme environment on Mars. So that's what we're talking about when you consider space robotics. Here's a lovely view of the Opportunity rover on Mars. You can see it's powered by an RTG, a radio thermoelectric generator. So it doesn't have solar panels per se. So it's got a very long life on Mars. And that allows it to move around, rove around, drill, dig samples, analyze, and send the equipment results back to Earth via its communications antenna up to a satellite in space around Mars, and then back to Earth. And that's how we're able to speak and control and communicate with the rovers. What's also important is software on the rovers. We need hardware and software. This is a view of the next rover that's going on to Mars. Perseverance is the name. And that will be looking for signs of past life, but also you can see it's of a similar design to Opportunity. Here you can see the rover tucked in the aeroshell. It's made of two halves, a bit like a clamshell. That bottom is the heat shield, and the top bit is the bit that contains the parachutes and also the sky crane. So this is the assembly just before it enters the atmosphere. It will enter the atmosphere and separate, and then you'll see that sky crane. Now, we've obviously been roving on Mars for quite a while. This is a very early shot of some small rovers that were in the late 80s, and we have Spirit and Opportunity also on Mars. So we have different rovers, we have different landers, and there's plans to send future rovers and landers to Mars from Earth. Here's a view from Mars. This is a view from one of the recent landings on Mars. And here you can see the Mars surface and the different robotic elements, the arm and the Mars environment. Very dusty, extremes of temperature, completely different from space, of course, and the rovers have to operate in space and on Mars. There's also another interesting thing happening. So Perseverance rover is carrying this Mars helicopter. It's also a robot, and it's designed to fly off autonomously. It's got a solar panel on the top of it, and it's got a counter-rotating gyrocopter that will allow it to fly up, land back down again, recharge its batteries, and will be able to help the main rover, Perseverance, go and look for targets of opportunity. So be very exciting. Watch out for the first Mars helicopter. And the helicopter and the rovers will help also discover things in ice craters where there could be some interesting things to look for, past life. And these are the sort of destinations that we're sending these rovers and helicopters to have a look at on Mars. There's another Mars mission that's going this month. It's an orbiter. It's also a robot because it has sensors and actuators and can itself operate in a space. So this satellite is also a robot, and this satellite is called Hope. It's been built by the United Arab Emirates, and it's going to be launched to Mars on a mission later this year, and it's going to have, this month, and it's going to have a look at the atmosphere and environment on Mars. Now I'm going to talk about the moon. This is an actual color photograph of the moon, and it's an amazing picture. And we're also going to have robots on the moon soon. We already have robots on the moon. So obviously we've been before with astronauts in robotic devices, landers, and we've had rovers that they've driven around on Mars. And we've had some fantastic images from the surface of the moon, but it's going to get very exciting in the next few years and months with the return to the moon. So we're going to go back to the moon with different types of rovers, different types of landers, and we are setting up a moon base. The different nations around the world are going to do that with us. And these are some of the interesting robotic things that are going to happen with the human and robotic operations. Here's a similar concept to a sky crane delivering heavy equipment now to the moon's surface. And there we'll be looking for different resources, looking for different things that we can mine, water, and also heavy hydrogen that we can also use here on Earth. There are also plans with SpaceX to go back to the moon and establish a moon base. So here you see the Starship version for the moon. They have a Starship version for Mars. And this one is designed to land on the moon, which has no atmosphere. The one on Mars has an atmosphere and is a slightly different design. Here you can see a concept for the automatic robotic landing of the Starship. So the Starship itself is a robot. It's a robotic launch vehicle, and also it's a robotic spaceship. And that lands and takes off automatically. And here you can see the concept for a moon base. Obviously, in the next few years, we're also going to see some humans and robotic landers on Mars. And I'll show you some of the videos for that. And there is an exciting new space station that's going to be built. It's called the Gateway. This is going to be orbiting around the moon. And on there will be also robotic arms and other robotic devices that will show how humans and robots can work together in space, but increasingly in the solar system as we move out from the surface of Earth, close by the moon, and into the orbits of Mars and other inner planets and outer planets. Here is the robot that's going to be on the Gateway, as it's called. It's called Canadarm 3, so it's the third version of the Canadarm. And here you can see its different joints, its sensors and actuators, similar in design to Canadarm 2 and DEXTRE, which I showed you earlier. And this will help the astronauts and cosmonauts and other international astronauts work in the vicinity of the moon, as opposed to low Earth orbit around the Earth. And here the robot is used to help move large pieces of equipment, but also smaller pieces of equipment. And the idea is that with the landers, we can set up the moon base, and these different elements will also have robotic operations and also work with astronauts, with the control either being autonomous, they work on themselves, or they're also working with the astronauts in cooperative robotic operations, where they work hand in hand together. So we need to design robots that can work on the moon themselves, but also interact with the astronauts. So it's very important that we think about how they're designed to make sure that they are designed in a safe way that we can work with them. We also can have robots on asteroids. So this is a satellite that's designed to go around an asteroid and look for heavy metal. This asteroid is completely made of metal. It's a big one. And there's a mission coming up soon to go and discover what this metal asteroid is all about. Some people think it's the remnants of a small planet, and that's the core of the planet that's left. It's very rich and concentrated in iron and nickel and other heavy metals. And there's a robotic probe that's going to go and look at that asteroid. So we do different launches from Earth, and we're going to explore the solar system, whether that be the moon, whether that be Mars, whether that be the asteroids or the outer planets, or the moons around those outer planets. So we have different launch vehicles that take us off Earth. Where I've been working in my career, I've managed to launch satellites from different bases around the world. Here you can see Ariane 4, Ariane 5, and Delta's rockets. And these rockets enable us to get the robots into space against the gravity of Earth. And then we can operate those robots off Earth, but you need to get them off Earth initially. So we launch them on rockets, as you probably know. And here is Ariane 5 in French Guiana, in Kourou in South America, being rolled out for a launch. You can see the rocket there with its two boosters, and the satellite is contained in the fairing in the top part of the rocket, getting ready for launch. And when we're ready for launch, it fires off, and then we can operate those robots in space. So we use different launch vehicles around the world. There's lots of development of robotic launch vehicles as well. So I worked briefly on this European Space Agency Skylon study contract, where we have a horizontal space plane that's being developed to take equipment into space, take off horizontally, and then go vertically into space, and then back down again and land on a runway, and it's reusable. So this is called the Sabre rocket engine. It's an exciting development that's happening in the UK, the United Kingdom, and they're testing the motors in Oxford, near London. And in the next few years, expect to see some big news about Sabre and the Skylon or derivatives of this type of vehicle. There's also robotic unmanned space planes. Here you can see the X-37 or X-37B. It's launched on top of a rocket. There you can see on the left-hand side, inside the payload fairing, and then it's deployed into space. It does its mission. In fact, these unmanned space planes have been up in space operating for about a year and a half, and then they land automatically on a runway and then go up into space again. So this is another example of what we call like a space drone. You'll hear a drone is a robot, so it's like an automatic mini space plane. These are all different types of space robotics. So I'm now going to talk about satellite. A satellite is also a robot. A satellite is above the Earth. Got a beautiful picture there of Northern Africa and Europe with a satellite in space. The satellite has sensors, it has actuators, it has a brain, it has a computer, it can be controlled by itself. So it fits the description of a robot. And also we can control that from Earth. And I've worked on lots of different satellite programs. Here you can see the GPS satellite called Galileo. And I was working as an environmental test manager on this program, building and testing these satellites to launch into space. And a previous satellite project I worked on was called Inmarsat, the International Maritime Satellite Organization. So these are different satellites that orbit the Earth. And now they're very much in the news are small satellite constellations, where the technology means that the satellites are generally less than 500 kilograms in mass, and we have lots of them. So these satellite constellations are also robots, and there are going to be a lot of these in the news. You've probably heard about Elon Musk and Starlink, and there's another constellation of these satellites, which is called OneWeb. And these satellites provide telecommunication services for us, but they're also providing internet from space. So here you can see how we launch those satellites into space. They go into what we call a low Earth orbit. It's about 160 or 2,000 kilometers above our heads. And then they have an active mission that could be, say, 5 to 7 years. And because they're in a low Earth orbit, they gradually lower because of atmospheric drag, and they will disintegrate in the atmosphere, and we have to replenish the network. Other satellites that are in higher orbits don't come back, and they are in what we call geostationary orbit. But these satellites are in the lower orbit. Here you can see a CubeSat or a satellite being deployed from the International Space Station. So these CubeSats or small satellites can also be deployed, again, using robotics or humans, and we fly them up on the supply vehicles and then put them out in airlocks. Another project that I personally have worked on, which is very exciting coming up in the near future, is JUICE. It's a funny name for a satellite project. It's called Jupiter Icy Moons Explorer. Again, it's a satellite that's going to the moons of Jupiter. It's going to be launched in the next year or so. And that satellite or robot will explore the icy moons. And you have to protect the delicate electronics from the extreme radiation environment. So the environment around the moon, Mars, and around the Earth are different. Again, the environment is very important to consider in space. And this shows you that when you go to Jupiter, you have to take account of the extreme radiation. So here you can see the technicians and engineers building that satellite, JUICE, in the clean room. Again, it consists of different elements or subsystems in there. And you have actuators, sensors that make it work together with the brains of the satellite. Here's another picture of a satellite. This is the OneWeb satellite. It's very much in the news. You're seeing a lot of these small satellites. They're producing about 1 to 2 of these satellites every day. It's an amazing feat of engineering. So they're producing these currently in the US, and they may be producing these soon in the UK. And these satellites, like the Starlink satellites, will provide internet from space. These are also robots, okay? So satellites are robots. Here's another interesting satellite. It's a scientific satellite. It's called the James Webb Space Telescope. And this is an amazing satellite that will be deployed on the other side of the moon in a few years' time, hopefully next year. And this is a very complicated satellite. It's very big. It's a big telescope in space. Here you can see the people doing the activities of preparing the heat shield, radiation shield, and they're underneath the main reflector there. Gives you an idea of the size of this satellite. But what's interesting is this telescope is all folded up for launch, and it has to unfurl like an origami activity in space. And the robot, it's a robot, will be doing that automatically. And I was involved in an instrument of this satellite called MIRI. It's an imaging instrument at the heart of the spacecraft. Just wanted to show you a few details of that. There are 4 instruments at the heart of the satellite that will discover new science, a bit like the Hubble Space Telescope has done. And MIRI there on the left is the instrument that I worked on. And here you can see it being tested before it went into space as a complete assembly. And it's a very complicated instrument, and it has to operate at very extreme temperatures. 7 Kelvin, that's just above absolute zero. And these delicate instruments have to work for 10, 15 years in the cold, harsh environment of space. So here it's important to make sure it's technically, and that we make sure that all the elements of the whole instrument work together. And there are different mechanisms. Here you can see detail of what we call a grating wheel assembly, different optical and mechanical devices with electronics as well, that will eventually form part of the whole instrument. And these are very critical, highly accurate and designed devices. And these devices have to operate in the harshness of space. Here's another view of the filter wheel assembly, again with different optical elements there. And these again are mechanisms that have to operate reliably. And I wanted to show you a robotic deployment video of James Webb, which will be deployed on the far side of the moon. And this shows you how complicated robotic devices are in space. So here you can see an animation of how the James Webb Space Telescope will actually deploy once it's launched into space. These large sun shields come down, and then it exposes the primary mirror. The mirror is folded to launch it into space. It's now being deployed, and the 2 side bits will all deploy as well. This is the radiation shield being slowly unfurled. Very thin and delicate and made of multi-layer insulation, and it protects it from the heat and light coming from the Earth, the moon, and the sun. And it's being slowly deployed, as we can see, automatically in space and being tensioned. The size of that deployment is about the size of a football pitch. So this is a big, big deployment. And then it has a multi being deployed. Here come the main parts of the telescope deploying. Automatically, the side bits of the main reflector to reflect the light from the deep universe. And here you can see almost deployed the complete spacecraft, which will be observing the universe on the other side of the moon, well away from any contamination of heat and light from the Earth, moon, and sun system. So this is a very complicated satellite, which is very interesting to see how it deploys in space. There are other robots moving on that will go to different planets, and we've already had this opportunity to see some of this. Here is a robot that was launched by the Russians to Venus, the planet Venus, which has very difficult, harsh atmosphere and pressures to get a robot onto the surface. They succeeded. That's an artist impression there on the left of what Venera 9 looks like. And there you can see the picture it took. It only survived about 20 minutes, 30 minutes before it was collapsed due to the pressure and the extreme environment. And that's the picture it took of the surface of Venus. So we can devise and design these robots to do exploration and look at different parts of the solar system. Here we are looking at the asteroid and comets around in the solar system, and another robot that was sent to have a look at that called Rosetta. You may have heard of that. Rosetta there is the big spacecraft that you see on the top, and it had a daughter lander robot, which is called Philae, and they were recently controlled by the European Space Agency and landed on the surface of a comet. Very unpronounceable name of 67P Churyumov, or something very difficult like that to say, but I'll try my best to say it. So here's another example of robotic systems with a satellite and a lander using robotic technology to explore the universe. Here's another example. This is the satellite called Cassini, and that's the main satellite. And that gold dish is the robot lander inside there that's called Huygens, or the Huygens probe. And this was launched into space. Here you can see the Huygens probe heat shield being applied in its final preparation in the Netherlands in Europe. And that probe was then launched, sent out to Cassini, with Cassini to Titan, one of the moons. And here you can see an artist's impression of how it descended onto the surface of the moon Titan. And there you can see Saturn's moon, a actual view of the image as it came into land. So it has valleys, it has mountains, and it has plains. The geography of the moon is like Earth, but it's made of different things. And here you can see the actual picture that the lander took, which it survived for about an hour or 2 hours before its battery died. And that's the view from the surface of Titan. Isn't that amazing? And that's the furthest robotic probe that we have launched from Earth out into the solar system. So it's landed on Saturn's moon Titan. And just imagine how we control that robot and make it work and we don't lose it. So I'm now going to show you some future space robotics. Here you can see a robotic submarine. So there are plans on the moons of Jupiter and Saturn to have a submarine robot that will actually go in the icy water that we've discovered underneath the moon's crust, and it will go underneath, dive down the crust, and then explore inside the moon's water ocean that we've recently discovered on some moons of the outer planets. Another moon that has one of these oceans is Enceladus, and also a couple of other moons. But Titan, you see, is there on the left with the Saturn in the atmosphere, and we have different ideas of how to get robotic submarines to explore underneath the crust or on the water. We're also trying to come up with ideas of how we could have drone robots deployed from lander robots so that we can go and explore them, a bit like the helicopter that we saw earlier on Mars. And these drone robots in the low gravity will deploy and help us explore not just from a fixed site, but could go and bounce around the low gravity environment on one of the moons where there may or may not be an atmosphere. So a lot of companies and organizations are developing robotics. There is an interesting organization in the UK called Fairspace, and we're working with them. It's called Future AI, that's artificial intelligence and robotics for space. And they are working to develop this space technology from the Fairspace Hub. And they're working to understand how robotics and humans can work together to do resources, do planetary exploration, and do things like work on the moon and do satellite repair in space. So they work with this different technology, and this is things like drilling, humanoid robots, a bit like the one you saw earlier, and also the rovers. And we're developing grippers and drills and autonomous rovers to be able to go onto the moon and to Mars. Here you can see some robots working together, controlled by astronauts. And here you can see different sensors and virtual reality and different control methods that we'll use with humans and robots working together. A very important part of robotics is vision systems, trying to understand what the environment is and what it actually is seeing with the sensor. So these are important technologies, the software, the algorithms, the hardware. So we're developing concepts to work in space and repair items in space, collect debris from the activities that we've already done in space. So robotics and humans in space are very important, also working on planetary bodies like Mars, like the moon, and asteroids and comets. So this technology is very interesting and very important, and there's a huge demand for this type of technology. Obviously, there's a lot going on in the environment of space, and you've probably heard on the news lots of things about Elon Musk and Falcon 9, Crew Dragon, etc., and Starship. So we've had some very interesting things happen in space in the recent years. We've had automatic landing of Falcon 9, and I think most of you have seen that. I'm going to show you that landing video because it is quite amazing if you've not seen it. So I'm just going to show you that video, automatic landing of the Falcon 9, and these are the Falcon Heavy rocket landing.
Side booster landing burn has started. Side booster landing legs have deployed. Landing zone. Side boosters have landed. Recovery operators move into procedure 11.100 LZ1, sections 4 and 5.
And here's a landing of the
Center core landing legs have deployed.
Which, if you remember, it didn't quite work, so that's why we have
the center core
loss of that center core. They did recover on a different mission. So there's lots of also robotic work developing with Starship. This is going to fly next week, so keep a lookout on the news. This is going to be a test flight from Boca Chica in Texas near Houston, and Elon Musk is going to test fly this prototype design. So watch the news for these automated flights, and eventually his plans are to have Starship flying, Starship design to take satellites and equipment and people not only to space, the moon, but also Mars. So this is an interesting development of reusable rockets that really is happening now, and it's a very interesting program to follow in the news. Here you can see a Starship docked to the International Space Station. This is not real. This is a simulated picture of what it would look like. You can really see how big Starship is in this picture compared to the ISS. Here you can see the Starships, three of them actually, landed on Mars with the beginnings of a Mars base. So we're going to have robotic devices, Starships, and lots of autonomous or semi-autonomous robotic vehicles, including landers, robots working on Mars in the near future. There is also the gateway, which I explained around the moon. And recently there was a competition to bring 3 landers onto the moon, and 2 of them will be selected as the final one to go and land on the moon. So 3 companies were selected by NASA to compete for this contract. And the first one here, you can see its concept. Here's the second one, and here's the third one. So they have different designs. And I'm going to show you this video of what the next couple of years is going to look like with those landers. And it's really exciting.
Being the world a challenge of the future. The door is now cracked, but the promise of that future lies in the young people, not just in America, but the young people all over the world. America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon in Taurus Littrow, we leave as we came, and God willing, as we shall return with peace and hope for all mankind. Godspeed to crew of Apollo 17.
Okay, so you can see it's a very exciting time coming up for going back to the moon, and I'm very excited to be watching that development. And now I've come to the Q&A session, so thank you very much for listening. Hopefully you've got some inspiration from some of the robotics that I've shown you in space, satellites, rovers, and different things like that, and also probes to deep space and some of the interesting human and cooperative robotics. And I'd like to thank you all for coming on this webinar with Aerotalks, which have been kindly organized by the Blida Rocketry Group. And thanks very much to Mehdi and Ramzi for inviting me on. And I'd now like to pass back to Ramzi for the Q&A session.
Thank you very much. Thank you very much, Mr. Raymond, for the great presentation. It was both enjoyable watching that video. We are actually going back to the moon in 2024, and also it was very informative. You moved us from the previous launches, satellites and robots launched on space previously and the future in space. So thank you for the time you shared with us and your efforts. And tomorrow also we'll be talking about environmentally testing of satellite. So thank you very much, Mr. Raymond. So we are moving now to the Q&A session. A lot of questions to you, Mr. Raymond, today. Be prepared.
Okay.
So to recap to the new joiners that have just joined us, to recap, what do have a robot do with space briefly? What do have a robot do with space briefly?
What? Sorry, say again. What
do have a robot to do with space?
Robots have everything to do with space, because without the robots, we wouldn't be able to go into space. So in my opinion, robots will be with us very closely for the future robotic exploration and human exploration together in space.
Also with extreme condition, temperature, radiation, I think that robots has the main factor that protect the robots is the heat shield. Is that okay? Is that right?
Yeah, depends. So if a robot has to work in space, then it will have to have protection from radiation, extreme of temperature. It has to have the right material. But then if it's on Mars, it doesn't have a vacuum. It's a pressurized environment. It's got an atmosphere. Maybe it has to have protection from the dust. If the robot has to go on a moon of Jupiter or Saturn, then it will have to be underwater. So it has to be like a submarine. So the robot design will depend on the environment that it goes into.
Talking about robots, you explained during your presentation landers and rovers.
Yes.
Yeah. For the new journalists, could you please re-explain it briefly about the difference between the landers and rovers and how do they work together to achieve the missions?
Okay. So a lander, as we call it, is launched from Earth into space, and then it goes to whichever object it's going to investigate in space, of course. And then it will either land on the object or through its atmosphere directly. And if it lands and it stays fixed, we generally call it a lander, a bit like the Viking missions in the mid-70s, Viking 1 and Viking 2. And also there are some landers that we recently put on Mars at the poles, and they stay fixed. A rover is a lander with wheels. So basically the rover can move around. It can be small, big, or whatever. So Opportunity, Spirit, Perseverance, the one that's about to launch this month, are examples of rovers. But you also have a rover, don't forget, on the moon, which we drove around on the moon landings back in the 60s and 70s. So a rover can be unmanned or manned, depending on how you want to use the rover.
Okay, so what kind of material used in the wheels? So a lot of I received a question from the public. What the materials used in the wheels of that rover?
Good question. So there is on the moon there is no air. So on Mars there is an atmosphere, but it's carbon dioxide, nitrogen, and some oxygen. So depending on the environment, for the moon, for example, they made the wheels out of a mesh. They didn't have a tire with pressurized air in it because they didn't need it. So they designed a mesh which effectively was open, but could actually roll over different rocks. But they had to design it very carefully because the mesh has to not get stuck. It doesn't have to get dig in the lunar soil, or regolith as we call it. And if you've been following the rovers on Mars, some of the rovers there have a slightly different design. They don't use a mesh. It's like metal plates. very lightweight metal alloy plates with an open rim. So it's not like your car, it just has a rim and a hub and the metal around it. And they've designed that with little bumps on that actually digs into the Martian surface to provide the friction. Sometimes that can spin and sometimes it can not work. So each wheel has independent control in order to get out of if it gets stuck, like in sand or heavy mud or something like that. So the Rover wheels are made out of different materials depending on the environment they're going to. So the Moon Rovers are different to the Mars Rovers.
Okay, great. Thank you for the explanation. So you mentioned also that robot can be controlled remotely or totally autonomous.
Yes. So there's two ways of controlling a robot remotely. You can control that what we call semi-autonomously. So you send a signal between the operator and the robot, and that signal has to send there, be processed, and then be sent back. And what we call the feedback loop is how we control the robot. The robot also has intelligence in it or on it in the form of computers and has logic. And that computer brain has software that we can update. And that logic, the computer program, can allow it to do autonomous operations. When the robot finds there's a problem, we can also interact between autonomous and semi-autonomous operations. So depending on the need, the robot can switch between being controlled by an astronaut or cosmonaut from the ground, from Earth, or to control itself in the location. And it depends on that by the logic it sees with its sensors. So it senses the environment and its control programming tells it whether to switch between autonomous or remote monitoring or semi-autonomous control.
So Ray, I think Ramzi has a problem with his connection. I will continue the questions. So a personal question from me will be that what are your thoughts of 3D printing? We've seen like new companies have started working on it. There is like this company in the US who are trying to completely 3D print a rocket. Can 3D printing used in space, or is it difficult or something?
3D printing is amazing. It's transforming the way that we will do work in space. In fact, whether we 3D print elements or parts for a rocket, that's already happening. So that, as you said, there's companies in America that are 3D printing whole rocket engines, whole elements of the rocket design. The recent launches from Rocket Lab in New Zealand, they have a 3D rocket printed design called Electron. Elon Musk is 3D printing his parts for Falcon 9, etc., etc. So 3D printing is great for rockets, and I believe we will be able to press a button soon and then 3D print a rocket. Yes, so we're not quite there. We still need to be careful. But we also have 3D printers now in space. So we have a 3D printer on the International Space Station, and the astronauts and cosmonauts can print out tools and equipment that they don't have. They don't need to send it up. You send the instructions on Earth, and then they can get that 3D object printed in space. And for future operations on the Moon and Mars, we're going to use the lunar soil and the Martian soil, and we're going to 3D print structures, habitats, solar panels, things before we get there, so that we can help us live and work on the Moon and Mars. So 3D printers will be sent first with the robots. They'll go and gather and do their little activity together, or they may operate in swarms. You may have swarms of robots 3D printing together and then building them and building the Mars base before the humans arrive. And that way, the risk is reduced of failures on Moon and Mars. So yes, 3D printers will be critical for the exploration of space.
So, in case of any failure on the robot mission, is it prepared to adjust to problem, or like radiation on extreme temperature? Is it all robots manufactured by the space agencies launched on space? Is all of that any failure, any problem in them?
It's a very good question. So we can design as much as we can as humans for the environment, but sometimes we get the unexpected. So generally in space, we have different levels of what we call redundancy. So, but sometimes you can't replace everything. So if you have a gripper or you have a wheel, you may have a spare gripper that you can take if the gripper fails, or a spare tool. But sometimes you can't replace everything. You can't replace the complete rover, for example, if you're on Mars. So what we try to do is build in redundancy at unit level, component level, subsystem level, and system level. So redundancy is really, really important. But at the end of the day, you have to say, what's the cost? What's the risk? And then you have to design a system that will try to work in those environments. So sometimes you'll have spare parts. Sometimes you'll have a spare circuit, like an electrical circuit. And sometimes you will have a completely spare unit. So the redundancy could be at unit level, component level, or system level. So depending on the level of redundancy, depending on the environment that that's going to go into, something might fail because of the radiation, as you just said. Something might fail because of it's just broken down. Something might fail because something unexpected happened. So we try to design for everything. But the clever thing is with robots and things we send into space, because it's hardware and software, we can reprogram the robot. So as we learn, we can reprogram and adjust the robot to its environment. And that's what we do with the deep space missions. We're constantly adjusting them, tweaking them, sending new software via the antennas and via the communication subsystems to the satellite, and we update the software. Basically, we do software upgrades every month, 2 weeks, every year or so. And that way, the old hardware can be kept running and adapt to the new environment. And it's also critical for the safety of the mission.
Is it all because is it all because the industrial IoT from space, or it could be controlled from Earth?
You can control from space or from Earth or locally, yes. Or the robot could control itself, yes. It depends on the what we call operational scenario. So if you're working with a robot on Mars, you need to interact with it. So maybe you have touchpad command, maybe you have voice command with the robot, or maybe you're working with people who are on a space station above Mars or in the Mars habitat or on Earth. So the robot will need to have different communication links to the astronaut on Mars, in space station, or on Earth or in the habitat. So yes, that will have to happen.
So for that, we are using the artificial intelligence in all of the mission we have already done. So we are using artificial intelligence and also, I think, deep learning for the machines, for the robots.
So robots can use machine learning or artificial intelligence, as it's called. So machine learning and artificial intelligence are almost the same, but they're a little bit different. So we use algorithms, computer code, to allow the robot to do its job. And the algorithms can also be adjusted. With AI, the machine is learning from its environment. So by doing different activities, it will learn and adapt for the environment. And that's the difference between just a normal algorithm and machine learning and AI. So we want to empower the robots with AI and machine learning so that they can be safer to use and also cheaper, faster, and they can do that a lot faster than we humans can. So AI and automation is really important for robotics in space.
Okay, thank you very much. And if you just have to say that what type of energy that robots use in their mission, in their way to point B, let's say point to Mars, what type of energy they're using, and what type of energy they're using when they land on Mars?
Good question. So you need electrical energy for the robot to function, and that energy can come from the sun through solar radiation. And we can use solar panels like we have on satellites and also solar panels here on Earth. And we generate electricity from the satellite or the probe or the robot. If that's not enough, or if the robot's inside the satellite, we have batteries. So we have nickel cadmium, nickel hydrogen batteries that are designed to be charged by the solar panels on the way to Mars. You can also use the thermal decay of nuclear fission, so they're called RTGs, radio thermoelectric generators. These are heat sources, small little fission reactor that generates the electricity and on the way to Mars and also on Mars. So for example, that picture of the rover that you saw, Opportunity, and the next one, Perseverance, that's going to be launched this month, they have a very compact, basically a nuclear generator that allows it to stay on Mars for 1.5 years without getting solar panel energy from the sun. So these are important things. Do you generate it locally? Do you make solar panels on the surface of Mars once you get there with robots to generate more electricity? So you need electricity to function. Yes, absolutely. And you either use solar panels, batteries, or these generators.
Thank you very much. And I saw that in the last part of the presentation, you talk about small constellation satellites. Is the future, in your opinion? Yeah.
So small satellite constellations are now. They're also in the future. So these are around the Earth, close to the Earth in what we call low Earth orbit. And these satellites are quite small. So they're less generally than 500 kilograms. It's about the size of maybe your kitchen table at home or something like that. Or it can be as small as a cube, 1 10-centimeter CubeSats. And these satellites are many, and they move around the Earth. And with a constellation of these satellites, we can provide services for us, such as telecommunications, or they can have sensors and they can do Earth observation, or we can send a constellation of satellites to Mars and we can have an internet around Mars, and we can send all the data between Earth and Mars with these constellations of satellites. And you've probably heard 2 key names recently, Starlink, which is Elon Musk and SpaceX, and the more recent one is OneWeb, which is another one. And there's a few other satellite constellations, like ICEYE is another one, which look back at the Earth, providing views of the Earth from space.
Great explanations from you, Mr. Raymond. Mr. Brentwood, if you have any question for Raymond.
Yes, I would like before to say hello to Mr. Raymond. And here in Nigeria, it's very hot, you know. It's sunny and hot. Okay, your presentation was very, very interesting, and there is a lot of information that you have given us. And I think this information brings us a lot of things, but it's not enough to give it in a small times like that. So I hope that all the audience have understand what we were talking about in this presentation. And for me, I have a little bit question, and I will start with The first question is about the interaction between human and the machines. So we build the robots, and we build something that we are using in space, but we have to train. We have to train the human to use this machine. And
right.
How can we trigger the brain of the human to be adaptive with this device, which is outside him? And there is a big problem, and I think the parts of the financial part is in here. How can the human be adaptive with the machine and the use of the machine? So what is your opinion about this this thing? I mean the adaptivity and the interaction, the machine interaction with human.
Okay, very good question. So when you saw the pictures of the astronauts working with the robots, they don't just work with them and say, oh, I'll just move the robot. They have to be trained. And this is extremely important because they're working with critical hardware. And also you need to train somebody. It's like driving a car. You can't just drive a car immediately. So a lot of time is spent in simulators on the ground where we train the astronauts and cosmonauts, and then we put them into the operational scenarios, and we also monitor how they progress. So we look at the feedback loop of how they interact with robots, and things are developing very rapidly in this area. So the initial robots you control just by sending a command to the rover or the lander on, say, Mars. On the International Space Station, we have that robotics workstation. Do you remember seeing that robotics workstation with the flight controller style joysticks? So we have to train the crew, as we call them, the astronauts and cosmonauts, how to use the joystick, but they get the feel of how to use it because they're trained with the feedback. It's iterative. It's just like a simulator that you fly a plane. So you gain experience and then you go fly the plane. And we certify the crew if they are able to do it. We also simulate malfunctions, and also we do errors. So we see how they react in real time. And what's really important is what we call situational awareness. They have to take in information, they have to look, they have to hear, they have to feel. Another of the pictures I showed you was of the exoskeleton. Do you remember seeing the exoskeleton? So with the exoskeleton, we have what we call force feedback. So with that, you can actually get to feel, touch almost, what the robot is feeling. So we have sensors on the robot. Those sensors come back to the astronaut through the force feedback or haptic control. You might see that word, H-A-P-T-I-C, haptic control. And that's where we feel the force generated as the robot is doing the activity. And this way we can completely interact with the robotic environment. So we don't destroy something, that the robot doesn't do something the wrong way, but also that if we need to adjust, you talked about how can we adjust in real time or semi-real time, then that's how we do it, by this force feedback control loop. And that's where the exciting thing has happened, that the processing time with electronics and things like that is, and with AI, is we're able to really improve the interaction between humans and robots. And that will only get better in time.
Thank you, Mr. Ray. My second question is about the control. For example, for the rover. So to control the rover, it's take a time between the transferring the data from the Earth station, the control Earth station, and the rover. So how can we manage this this lapse of time to do any task for the robot. Maybe he will go. He is going to make a movement, but this movement will bring him to fall down. But how can the robot now feel that it's very dangerous, it's dangerous, and he will take a safe position until he got the next instruction? So it's the question, because it takes time to get the feedback, to launch the instruction and get the feedback, and what is the devices used and how we can manage that.
Okay, so you've identified a very key thing which we have to understand about space robotics: the time it takes from a signal to go from the transmit to the robot and then receive, process, retransmit, and then back to the operator. That route is a forward and a reverse loop, and that takes time. So yes. I'm gonna ask you a question. How long does that take to go to orbit? How long does that complete time take to send that signal to orbit? Do you know roughly?
I don't know.
Okay, it's in the order of a few seconds. Okay, how long does that take to go to the moon? That complete signal and return.
Maybe one minute. No.
2 to 3 minutes. Yes, the complete. So there is a time delay.
Okay.
How long does it take to go to Mars and back?
So we can multiply this by 10.
So it's about 20-30 minutes, about half an hour.
20 minutes. Yes.
So that means when I say hello, that signal takes 20 minutes to get to the rover. Yes. Then the rover has to do something. Then the rover says bye-bye, and it has to send that signal back. So that is maybe 1 hour.
So it takes 1 hour.
It could do by the time to process. If the rover is in front of a crater, and as you said, if it moves forward, it will fall down. So this is so important, because you have what we call semi-autonomous and autonomous control.
Okay.
And this is the difference between autonomous. The robot decides itself with the environment and its sensors. And you have the software on board that says stop or continue. But also, if you are working with a robot with a human, either from the space station or on Mars or from Earth, then it's what we call semi-autonomous. And therefore, you have to use protocols in software that have to wait before the next instruction is sent. And you have to think about that first, because as you said, you could go down a hole. So this is important, that the robot knows when a situation is dangerous. So you have to empower the robot with sensors, but you also have to empower the robot with the logic, the algorithm, the autonomy, to be able to say, I don't like this situation, stop. And this is where there's a big revolution happening with the way that we process semi-autonomous or autonomous operations. And with the processing power increasing, but also with AI, we can get assistance with AI. We can stop the very slow operation. We maybe can go faster because the AI learns. So the robot learns over time that it can do things because it's already learned the activity, but it's still operating within the safety boundaries of the activity. So that's how we do it.
It's interesting. So the other question is one you was talking about the energy, the use of the energy, and how to bring it from the nuclear source or a sun source, something like that. In the case of the rover, you state that he got a mission to bring material from this, Mars, Earth, and he have to drill. So the driller use energy, and I know that if we have to drill when we are in something which is as a rock, so you have to you have to make a big torque. So did the rover got something like I mean hydraulic motors to bring a big torque, or they still work with electrical energy only?
Good question. So again, I throw the question back to you a little bit. It depends on the environment. So if you need to operate in space, which is a vacuum, you can't use hydraulics because hydraulics don't
very big problem.
All the fluid or the oil will make little globules like you see on the space station. So it won't lubricate the joints or things like that. So if you're operating the joints on the robotic arms on the International Space Station, they are electrical joints, okay? So they're not hydraulic. If you're operating on Mars, you have an atmosphere. In fact, if you see this picture behind me, this is Mars. This is a sunrise on Mars, okay? So there is an atmosphere. There's a little bit of a pressure and it's very cold. So if the hydraulics is sealed, okay, you can actually use hydraulics on Mars. So you can similarly adapt, say, drilling techniques, but they probably want to use electrical because hydraulics could leak and it might not be a good idea. As you said correctly, something like drilling into a rock would need a high torque. So you need a lot of energy, in fact. So the rover on Mars takes the energy from the sun, recharges its batteries, but it also uses that nuclear battery, if you call it that, the RTG, radiothermoelectric generator, to provide it with enough electricity to do the critical drilling. So it always has enough and it doesn't run out of energy. And then it recharges itself with the solar panels, or maybe that RTG is big enough to provide enough energy for the operation. It's all about how you design the system. If you're working on the moon, again, you can't use hydraulics because there is no atmosphere. You can't use hydraulics on an asteroid. So you're exposed to the vacuum of space. So different environments dictate different robotic solutions. So that's the answer to your question.
So by the same token, by the same token, Mr. Blida just said, will the dust storm on Mars cause problems for the solar panel used on the rovers and landers?
Very good question. So the first rovers that went to Mars got covered in dust, and if you have the dust on the solar panel, it's not good. So you're going to have some problems getting the electricity from the sun. So what they found was that they have dust storms on Mars. So dust storms, and you have a wind on Mars. So there is actually a wind, and they have, like we have on the deserts on Earth, they have dust devils. And the dust devils spin, they're like a little mini tornado, and those dust devils are actually very frequent on Mars. They've been caught on camera. There's some videos. If you type in Mars dust devil, you'll see a video of these swirling winds with the dust. And the surprising thing is that the rover over time can get a lot of dust on their solar panels. But what happens quite a lot is that these dust devils go right over the top of the rover, and they suddenly, it's like a car cleaning activity. It just cleans all the dust off the solar panels for free. So if you drive to one of these dust devils, you get a free clean. So what they're trying to do is design mechanisms that can dust this off, like a bit like a windscreen wiper on your car, to dust this off, or brushes. But yes, it's a problem. The dust on Mars is very sharp. It can damage the surface of the solar panels and get in all the instruments. But also on the moon, you have dust, and that dust is electrostatically charged, so it sticks to everything. And they're very worried about mechanisms and dust on the moon as well as on Mars. So dust is a problem as we work with robotics, yes.
That exactly what was my second question. I was going to ask you, are they trying to figure out self-cleaning panels?
Yes, so you could shake it. You could do a little shake. You could tip up, tip down. You could also electrostatically charge, because the dust particles are charged. You could quickly charge and bounce it off, or you could have a mechanical actuator to remove the dust. All these things. There are no dust devils on the moon, of course, because there is no atmosphere. So you don't get a free clean on the moon. You only get a free clean on Mars. So again, different techniques, different designs for different environments.
Great. Going back to space debris, are they? So I received that question from Saleh bin Mitka. He said, "How dangerous space debris are for space operations, and what are the potential solutions?"
Very good question. So unfortunately, we've been polluting space since we first launched the first satellite into space. Sputnik was launched by the Russians back in 1957. And when rockets go up and they go into space, bits of rockets are left in space, or things are left, or you can have paint come off something. Astronauts' gloves have been dropped from different things. But also satellites, when they lose all of their propellant or their fuel, they're no longer operating. So we call a dead satellite. The problem is the speed at which these objects are rotating around the Earth. Now, the space station, for example, is moving at a very high speed. It's 17,000 miles an hour. Just think about that. It's zooming around. We see it there. So if that space station hits a small glove, a piece of paint fleck, it becomes very energetic and it can actually damage the space station. So it's very important that we keep space clean. And there are now rules, there are more rules to stop having debris in space, but it is a problem. And different heights of different orbits have different amounts of debris in. So if you're close to the Earth, there's a certain cloud of debris. If you're further away from the Earth, in what we call geostationary orbit, where there are lots of geostationary telecommunications satellites, you also have some debris, and there's some in between. And also, this thing is not moving in one direction, it's moving all over the place. So debris is a problem. We're currently taking action, and companies and organizations and the world realizes this is a problem. We have to protect not just the planet, but also space from debris. So they're designing things, satellites, different types of garbage removers, debris removers from space, but it will be an ongoing problem. So we have to design robots, satellites, all the equipment into space to minimize the debris when we launch it, when we use it, and when we are finished with it. So we have to think about that. It's not just the actual operation of the robot, but what happens when it's finished working, when it runs out of fuel or has no more electricity. And sometimes we can send the satellites back down through the atmosphere if it's close enough and it burns up. So some garbage removal designs are actually designed to attach to a satellite and bring it back down. But there are some other satellites that we can't remove. So this is a problem. And as we explore the solar system, space debris is going to be a big issue for us moving forward.
Yeah, as well as satellites, we are launching a lot of satellites in space, in low Earth orbit and beyond. So, are there any space laws about that?
Yes, there are. So, very good question. Space law is developing. So anybody that needs to launch a satellite into space has to get the authorization and the license from an organization called the ITU. International Telecommunications Union, ITU. The ITU is based in Vienna or Switzerland, I forget which, one of the two countries. I think it's Vienna in Austria, it might be Lausanne in Switzerland or Zurich, one of the two countries. And the ITU is the international body that regulates what goes into space. So if you want to launch a satellite, if you launch that into space without organizing with the ITU and also with your country regulator, your government, you go out of business because you will go bankrupt or you'll get fined. You won't be able to send it up, basically. Nobody will launch it. But the satellites in low Earth orbit, they must, that's a must, there is a law, space law, they must come down before 25 years. So if it's in low Earth orbit, there is a space law that says it must come back and burn up. If it doesn't, then the company will have fines and it will cost them a lot of money to operate. So the companies, organizations have to respect these space laws, and they have to get the insurance on the rocket to do that as well. So it's quite a big issue for companies to launch into space.
Thank you very much. I see Faris Elias have a question, or Mr. Bentrad a question for Ray. Either one of you just...
I don't know if Faris would like to say something. Let's go.
Yeah, in one of the pictures that you showed for the one of the robot arms that was that is being developed for the ESS, I saw an old computer in the picture. So because the International Space Station is so old, it has like multi decades in space. So is that an issue when you're designing a robot arm? So it has to work with the equipment up there?
Very good question, Faraz. Yes. So as I said in my talk, robotic systems have hardware and software. Now, when did you last change your computer, Faraz? Was it 2 years ago, last 6 months, 5 years ago? I bet it wasn't 20 years ago. Okay. And when did you design that system? Did you design that computer 25 years ago or 30 years ago? So the way we design computers and the robotic systems is extremely important. For the control of the International Space Station, they use laptops. They use IBM laptops. They are ruggedized to go into space. They're also protected from what we call single event upsets, or SEUs, because we have radiation in space that can trick electronics with charged particles, and it can cause some memory problems. But those laptops are used as the primary interface to control the robot with the joystick. That's what you saw on the robotics workstation, yeah? And those laptops have to work, but also software has to work. So that software may have a few bugs in it when you launched it in 1990. Then you updated it, we patched the software in 1995. Then we have a new upgrade in 1999, say. Then we have another upgrade in 2006, but you're still using the same laptop. So then you have to make sure that the software still works. So you can't suddenly say, okay, yeah, I've got Windows 10, Windows whatever, and then you can, but you have to think about that in the way that you design your robotic system. So you have to have modules that are effectively of software that are self-contained, that can be upgraded. And yes, we can change the computer. Of course we can. We can replace that laptop with a new version, and we can update the software on that. But in the meantime, the robot doesn't know that. So you have to make sure this problem is thought about and how you maintain. It's one of the most critical things, Faraz, well done, to maintain safe robotic operations, because you have to have safe, reliable software, and you have to have the software that works on the hardware or the laptops or the computer chips that are on the robotic device.
Thank you. Ramzi?
I was just so in I'm just actually checking the questions on our Facebook page. So I got a question from Abdelmoumen Khamkhoum. He was just asking about the software used to design robots to be launched later on the to Mars or just on orbit.
Okay, so we use software. We use all types of software. So I think it's a general question. So we use CAD software to design the robot itself. We will also use different software for the brain of the computer. Could be in C, C#, C++, Ada, in different software languages. It could be in machine code. It depends which operating system the robot is using. And software is always being used and updated right up until launch. So maybe you've used software to simulate the environment, the thing, and then you test the robot with software. You use design software to make it. You use manufacturing software to build it. You maybe use 3D printing software to make the 3D printing things. All of this involves software. And then when we have the software and the robot is launched, we use what we call operating software to do mission work. There is also mission analysis software to work out where to send the robot, mission critical software that's used to, for example, think about autonomous or semi-autonomous operations that was asked earlier. So all of this is software, safety software, safety critical software. So we need software engineers in all aspects of the project, from the beginning right through to the end and through the operations. And software is used in all parts of the project.
Yeah, thank you very much, Mr. Ray, for your answer. Is there any question from you, Mehdi, Mr. Benders? Because we answered all the Facebook live questions, and if there is a question just before.
I think I would like to notify something that have been done last year by the team when we was preparing to go to Spaceport Challenge in USA, and the rocketry team of Blida have an idea to participate with a payload, an active payload, and we was thinking about creating or making something that can collect the dust, the space dust, the space debris surrounding the Earth, but the small debris, especially the small debris, because it's not detected really by a radar or something like that. So we have think about a small CubeSat.
Yes.
Which is commonly have a propulsion system, and the second part is that we have called Pac-Man Space Duster. So it's something that's yes, it's like that. So it's something like that. They deployed like a hand of catching baseball. And when they track the debris, they have to trigger it and catch it, and after with this velocity, he can lose his orbit and come down to the Earth and disintegrate. So that's what was our idea, and we would like to work on it, but Spaceport have been delayed, and we stopped here in the idea. That's all. And these things have been brought by Ramzi, Nui, and Faris, and all the teams they worked on.
Very interesting. I've seen a design very recently similar to that. It's a CubeSat, and the CubeSat will sense. So the CubeSat is a robot. Okay, I said a satellite is a robot, and the CubeSat will sense when it is near debris. So it will have autonomy, it will have sensors to say, aha, I'm coming to see some debris. It will have sensors that are seeing this, and the optical, the infrared. It will use its intelligence to maneuver itself, and as it gets close to the debris, it will effectively, best way, you know, like the animal, the hedgehog with the spiky pines, it will then start to open up like strands of sticky material from the inside of it. It will start to deploy, and then this sticky material will then capture like a net, debris, and then it will then pull it down again, and then it will go to the next place. It will expand up and go back down again. So it will be like a sticky sponge collecting the very, very small debris, not like a Pac-Man, but like a sticky sponge. And the sticky sponge will then, when it has enough debris, it will then deploy a drag antenna type thing, which will cause the air. There's very, very thin molecules of air in low Earth orbit, and the orbital drag will then bring it back to Earth, and then it will be burning up. So it basically is like a sticky satellite, and the sticky satellite will then hoover up. It's not a hoover, it's not got a vacuum, but it will stick itself to the debris that you can't see. And that's a very clever idea. But I'm also interested in your design of a Pac-Man.
Yes, and in our design, we think that we use this hand made it by Kevlar, and all the composite things. That's when they go inside this screen. So maybe the small things can pass through the screen, but this, what we use as a composite material, is something which stick inside, and it's like the same idea, but it's very simple. It's open like an umbrella, and catch the maximum things that are catched, and afterwards they go down by the movement of the cinetic movement of the energy that impacted inside this hand.
I see. So it's a bit like an umbrella, and in the inside of the umbrella, you hold the umbrella,
we grew the arm. We grew the arm to make a couple. That's one stick. It's make like that, oops, and it's lose the orbits.
Okay, so a good idea is to use maybe a gel on the inside of the umbrella. Have you heard of aerogel? It's used on a couple of space missions to collect dust and cometry stuff. So you could use a gel that would take all of these small particles that would interact with the, the velocity would allow them to be captured by maybe a multi-layered gel or different materials, and then the inside of the umbrella would be like a hoover. That would be a clever idea.
Okay, it's interesting. Thank you.
A sticky inside of an umbrella. Yeah.
Thank you very much. Thank you very much. Yes, Ramzi, you have to.
Yeah. Thank you very much for this informative presentation, Mr. Raymond. And if you have another question from you, Faris, Mehdi, and Sheikh, please come on. So if not, I'm going to end this presentation and this live. Unfortunately, but fortunately, we will see you again tomorrow. So Mehdi, if you have a question, or Faris.
So Ray, I have one last question. Like we seen in your presentation, there were like those robots and the X-37, those, I'm gonna call them like drones.
It's like a space drone.
Are they going to be able to intercept and repair satellites, just like the astronauts did using the space shuttle with the Hubble telescopes?
In theory, yes. So they would be controlled to do different things in space. So another robot repairing a robot was the space shuttle repairing Hubble with the astronauts and the robotic arm. So there you had lots of robots, lots of crew. With the X-37, yes, it will be able to do that autonomously, we believe, yes.
Cool. Thank you.
Okay.
Thank you very much. Maybe Ray, we end this presentation with some Arabic words.
Oh yes. So I just like. Je vous remercie beaucoup d'être ici ce soir. J'ai beaucoup aimé d'être invité par la société Blida Rocketry Club. Ça m'a beaucoup aimé. Et puis, je vous me remercie beaucoup pour l'opportunité de parler ce soir, aussi demain. Je suis très intéressé de passer les expériences de ma vie dans le domaine de l'espace chez vous, là. Mais bien sûr, en arabique, il faut que j'essaie. Donc, je vais là. Shukran ala hudurikum. So that's my best.
Thank you. Thank you. It's great effort you do.
Thank you very much, Mr. Raymond. Dear audience, dear participants, fortunately we arrived to the end of this live, and hopefully see you tomorrow with another topic with the same guest, Raymond Stott, he will be talking about environmental testing of satellites. So make sure to be there with us tomorrow at the same time, starting from 8 p.m. to now. Yeah, we just run 2 hours live, and all that because you ask a lot of questions. And thank you very much. We are ending this live, and see you tomorrow.
Bye, everyone.
Bye.
Thank you.